Okay. So what I do expect you to memorize is also whether or not the amino acids are nonpolar aliphatic, nonpolar plain, nonpolar aromatic, polar amino acids, positively charged polar amino acids, negatively charged polar amino acids. I also want you to know how they're grouped as well. I am not concerned at this point that you memorize these single letter abbreviations. Okay, so only the 3-letter abbreviations and and the groups that they are in based upon their polarity and their structure. Does anybody have any questions on that?
When do we have the quiz over that? Memorizing them?
Probably not till after spring break. So.
How soon after?
Oh,
You
come
think
on.
that's the real question? Like the same.
Start making note cards.
Like we get
Start
to,
making note
like,
cards
back
and
from spring break.
I still
put them
have a
together.
lab report to write over spring break and a comp essay.
I will likely put together an online quiz this week. Yep.
No, but I need to get in my class.
I also have a project for you guys to do. Group projects. Okay. No, I'm moving on that.
Oh.
I'm doing something a little bit more advanced, a lot more advanced, actually. And I'm hoping that we will turn this into a lab because I've actually done it. I've actually done it in grad school. And it's not something that a typical biochem class would do, but it's pretty cool. Okay? And hopefully we have the funding to do so. We'll talk about that in just a little bit. Putting together peptides, that's actually what the project is about, synthesizing peptides. When you put peptides together, what type of reaction has to take place?
Condensation.
That's right, a condensation reaction. I want you to also know that. How to put the amino acids together, what they look like when they come together. So what's actually going to condense? It's actually going to condense.
When the 2 amino acids come together, so an OH group and an H often usually OH off the, yeah.
Devin, do you agree with that? What do you think, Megan?
I mean, most of them have like an extra hydrogen on the amine group, so I'm assuming it's where one of the hydrogen's gonna come from. And then I mean, if you have the OH, it's probably also gonna come off.
But remember, this changes based upon what?
pH.
It changes based upon pH. Okay.
So you have to do the neutral pH, is that what you're saying?
So, based upon, it depends. It depends on if you are doing this in what? Acidic conditions or basic conditions. Now, in terms of synthesis, in terms of synthesizing these, you actually have to use protecting groups. And we haven't really gone over protecting groups in organic chemistry yet. Did you guys do protecting groups with Dr. Easton? A lot of protecting group chemistry? Okay, we haven't got there yet in organic 2. We're really close. We're really close. But you have to use protecting groups when you actually do this in the lab in synthesis. So we'll talk about that a little bit later. So it's the amine of one and the carboxylate of the other. And that's where the condensation takes place, and that's where the peptide bond is formed between the nitrogen and the carboxylate carbon. Good. We already went through and talked about the enantiomers. Talked about the amino acids with polar and nonpolar side chains. Talked about the rare amino acids found in nature. There's an example of the formation of the peptide bonds, which we just discussed briefly. And there's your peptide bond from the nitrogen from one amino acid to the carboxylate of another. And it's important for you to understand to try and keep your bond angles. Okay, so when you write out a peptide, which I will probably ask you to do, when you write out a peptide, I want you to be able to flip those and keep the correct bond angles accordingly. Okay, so it doesn't look all wonky and weird. Now, today you are definitely going to see some wonky and weird peptide bonds in just a little bit. Okay, and that is simply just based on constraint and the size of the overall molecule. What do you know about peptides and their charges, just like amino acids, just like proteins? What do you know? What can happen? Okay, so they're electrostatic, based on their electrostatic environment, they're going to adopt different charges in different locations. Okay, so here's an example of a peptide. What's overall charge on this one? Cody? What's the overall charge on this one? Delcor, sorry.
On that molecule?
On that molecule.
+1, right?
Look again.
+2?
It's +2. Okay. Kylie, what would give it a +2 charge? Why would it be a +2? Okay, you pass. That's fine. Avery, what do you think? What would give it a +2 charge? What kind of conditions? Megan?
Wouldn't it be acidic conditions?
It would be acidic conditions, okay? The carboxylates already have the protons on them, right? The amines have extra protons on them, and they're at a +2 charge. What pH do you think this might happen at? Caleb?
I'm gonna say like 6.
Probably above that. Yeah?
6.5 or like you're closer to 7.
Or I mean above that.
Well, cause you're.
Oh, okay.
Acidic
Oh,
conditions, more acidic below that,
I was-
excuse me.
I was just thinking like in the body. I didn't know if you get much lower than that in the body.
Again, I'm just putting this out as the peptide.
Oh, okay.
So not higher, but more acidic than
Gotcha.
6, which would be lower on the pH scale. Excuse me. Yes, ma'am.
Wouldn't it have to be done then in the body in acidic conditions? Because otherwise you wouldn't have an OH to pull out or an extra hydrogen to make a water molecule. So I
So
mean, in the ribosome, it's acidic.
it's a good question. If this was a drug, you would want to make it as close to physiological pH as possible, right? You know, I was telling you about my son's drug, which is also a peptide, and it's 6.5 going in, which burns, but it also makes certain that the peptide's probably in the correct charge state that it needs to be.
Well, once the bonds form, the pH wouldn't be as significant as before the peptide bond is formed.
I would say that's probably dependent. I would say that's dependent on a few things. We already covered this. Let's take a look. Polypeptides are polyamphylites. What are polyamphylites? We covered that in chapter 2.
Have both positive, or both positive and negatively charged functional groups.
Yeah, they can have both positive and negatively charged functional groups. Okay, so here the carboxylic acid proton on the free glutamic acid is then dissociated, and you can see that up there. And that happens, it's basically saying here 4.2. Okay, now this is in an electrostatic environment that is not being manipulated right now. But what would happen if you had another amino acid residue or another peptide in proximity to this, or protein in proximity to this? How that might change? How might that change?
Can you say that again?
Yeah, so we're just looking at this undisturbed, okay, by itself. what might it look like if it was in a microenvironment where you had other proteins or peptides around it? Okay, so maybe you could consider bonding. What else?
Like a hydrogen bonding, like that's where it's impractical and others are actually like.
Okay, so hydrogen bonding. What else?
Electrostatic interactions.
Yes. So what kind, in terms of electrostatic interactions, how might it affect this dissociation?
I think it harder to happen.
It could make it harder to happen. What would it take?
Like to make it more difficult, or what would it?
Yes. What would it take to make that more difficult?
Putting it in a solution, or like, if it's slightly acidic in your body, it'd be harder to decode it.
Okay. So if this was in the presence of an acidic group, right, then you would think that the basic form would be harder to form, right? Because that proton then would not want to dissociate, right? Good, good. So take a look at this. Look at this unfavorable electrostatic environment. What would you gather from this? Gather from this.
Is it because there's a negative charge on that oxygen that it's more likely to eliminate?
Okay, but look at the arrows.
It's more likely to stay on there. That's the major product, right?
So why?
Oh, because even if it does come off, there's two places where it can bind, so it's twice as likely to bind to an oxygen. Because even if it doesn't go back to the one it was originally on, it would just go to the other molecule.
Yeah, that's correct. That's correct. Plus, you also have to consider that you have two negative charges trying to be next to one another too, right? Negative and negative should do what? Should repel one another, right? How about this one?
The negative and positive stabilize each other. so-
Yeah, yeah, exactly. The negative and the positive stabilize each other. Yeah? So just being aware of these types of microenvironments, I think, is important. Just understanding how these charge separations occur and what happens during that process. Here's a titration curve for that tetrapeptide that we looked at earlier. Take a look at the pKa here. Look at this. There's that +2 charge that we talked about. And look, we're way low. So it's going to be really acidic for that to have that +2 charge. As we make our way closer and closer to the isoelectric point, you can see that you end up with a +1 charge, and then we keep moving on up until we get to the -1 and the -2 charge. Again, being closer to physiological pH and being more neutral, clearly that's more ideal. Let's switch gears a little bit. I apologize. Let's switch gears just a little bit. And let's take a look at some antimicrobial peptides.
That's an antiviral. This is the beer going in.
Okay? But it's also antimicrobial. Okay? Some of these can serve as multiple functions. Okay? Is there a peptide bond in here?
Yeah.
Yeah, there are. Are there any natural peptides in here? Or natural amino acids in here?
On the top right, maybe?
Maybe, not that I'm aware of. I can't really pick it out.
Aspartic acid.
The one,
what are typical AMPs? What are typical antimicrobial peptides? What are they? What are they?
The ones with the long chains?
No, general classification. General classification. Because really what we're looking at is protein synthesis, right? Eventually, you get in the body, we're talking about amino acids going through translation, right? And eventually you get through the ribosome, you make polypeptide, and then you get a protein. But I wanted to just kind of change gears just a little bit because peptides are also used as therapeutic agents, therapies, peptide therapies. So maybe this will help you. I told you they would start getting a little wonky. You see in here, they start getting a little bit wonky. Okay, so this one definitely has some unnatural stuff to it. Okay, what atom in there is not really often found?
Phosphorus?
The
Oh, it's
chlorine, the halogen. Yeah, so there's several chlorines. There's several chlorines in here. What I found really interesting about this one is that it has the phosphate down there on the bottom right, but it also has the really polar tail out here on the end. So would you consider this, or non-polar tail, so would you consider this still be like an amphiolite?
I think it would react far more hydrophilic.
Yeah,
Because of the
there's-
sheer amount of oxygen.
Yeah, look at all those oxygens and nitrogens, right? Yeah, but its molecular weight is really heavy, that's right.
So what makes this antimicrobial? Because like in organic in our chapter is talking about a lot of alcohols are that because they have long tails. It's happened to.
So are you trying to get at the fact that antimicrobials are synthetic mostly?
No,
No?
because many of them are found in nature. Many of them are found in nature. I'm looking for a general classification that every one of you knows in here. We'll keep going, see if you can come up with it.
Maybe it's a little
This
too
one's
general.
probably gonna give it away. Bacitracin. What is bacitracin? Never heard of bacitracin?
I have.
Antibacterial.
Hold on. Have you, what's the Disney show with the nurse robot that's the big
Big Hero
I'm
Six.
supposed to
Baymax?
Big Hero 6.
Big Hero 6. How
Oh,
many
yeah.
people have watched Big Hero 6? Okay,
That's right.
bacitracin. You're allergic to bacitracin. What did he spray on his arm?
That's the trace.
This bacitracin, it's an antibiotic. So these are antibiotics. Okay.
That's what you've been asking.
Well,
Yes.
That's on the slide.
Antimicrobial is on the slide.
well, but the first one was antiviral. So
It
how
is,
is there-
but what I'm saying is some of these are also, they serve multiple functions.
Okay.
They serve multiple functions, okay? So, antibiotics, many of these are polypeptides, okay? Look at this one. This one has a cyclic component. You see it over here on the right-hand side. And then it has a linear portion. What are you looking at? I thought you were looking something at. You're on your computer.
something that I didn't.
Okay.
Wait, what were you asking? Were you
If you recognize any of these as
Oh, I thought
antibiotics.
you were asking about like what about them?
Yeah.
I knew they were
Yeah.
antibiotics. I thought you were asking about what about the chemical
That's what
structure
I
made them
thought.
antibiotics.
No, that's why I said a general classification. No, not based upon their structure. So,
But do they work in antibiotics because, like, everyone that you showed us is very electronegative atom rich. Is that like why or?
that's a great question. I think that they're organic. And many organic compounds as therapies contain nitrogen and oxygen, sulfur. what I was saying earlier, you just don't see like chlorine, fluorine, you don't see halogens as often
Yeah.
in those types of therapies. Sulfur is common as well. But we also have to think about solubility, right, and how it interacts in the body. Your drugs that are orally bioavailable, all of your drugs that are orally bioavailable will be water soluble, okay? The ones that are not will be taken how? Lipid soluble, so they're either going to be intramuscular injection or an intravenous infusion, right, by IV, which nobody likes. All right, so there's daptomycin. This one's got some free carboxylic acids floating around in there. Still high molecular weight. There's another one. And there's vancomycin. Vancomycin's fairly more common. People have heard about vancomycin. It's actually been around since the 1950s and 60s. I actually know the history behind vancomycin. I think it was discovered back in the early 1950s in Borneo. It was discovered by an Eli Lilly researcher who was in the jungles in Borneo. And this came out of a soil sample in Borneo. It got its name from the vanquish or vanquishing bacteria, but I think he was working with someone who was there on a missionary stay, and that's how, anyway, that's how it was discovered. Does anybody know what vancomycin and some of its other derivatives are used for? Fighting MRSA. Yep. Yep. So there's the need for antibiotics or new antibiotics is really huge right now. Why?
We've gotten very good at fighting disease, but subsequently disease has gotten very good at fighting us.
Yeah, it's this molecular battle. I mean, it's really that, and really microevolution is the issue, is that we have mutations that happen and they get around the drugs that we've already developed. How can resistance be developed